Okay, 7.3, using counting methods to find probabilities. Wow. Counting methods to find probability. Alright, so section 7.2 was so-called what was it called? Something about counting methods, right? 7.2 was all about investigating counting methods, the factorials, the permutations, combinations, and the different techniques we considered there. And what we were doing in 7.2 was finding the size of various sample spaces. Whether we knew it or not, that's what we were doing. So recall that the probability for some event is just a fraction, right? If someone asks you what is probability, I mean, it's kind of a loaded question, but the simplest way to answer it is a fraction of, let me start with the top, the number of possible outcomes in some event, whatever event is being measured, over the number of outcomes in the sample space. And you may say, what's a sample space? Well, sample space is just the collection of all different possibilities for a certain experiment. So if I roll a six-sided die, right, then the sample space is the collection of all six sides, right? All the possibilities. How many possibilities are there when you roll a six-sided die? Well, there are six, right? There are six possibilities. That would be the number of outcomes in this sample space. Rolling this six-sided die, the denominator would be 6. The numerator would depend on whatever event you're trying to, measure. All right, so all of 7.2 was about finding the number of outcomes in the sample space. Again, whether we knew it or not, that's what we were doing. The whole point of using these counting methods was to figure out how to count large things, like how to count things, things pulled from groups for combinations and permutations and different ways to order things and so on and so forth. So what we're going to be doing in 7.3 is going to seem relatively easy because all of the hard work has been done in 7.2. All we're going to be doing here is actually finding probabilities for events that we were discussing, types of events we were discussing in 7.2. So let's see, let's start with an example. All right, so example 1 from the text, the text 7.3 says, suppose that as one of the 20 graduate students in the physics department, you have a chance of being selected for one of the 3 student spots for a conference trip to Cancun. So the number's 20 is that's standing out to me because that's the total group, right? And the number 3 is standing out to me because that's how many spots there are available for this particular trip. If the names of all the graduate students were put in a hat and 3 were drawn, what is the probability that you and your 2 friends, Leonard and Sheldon, end up being chosen? All right, so I'm not going to write all that out, right? You can read it in the ebook. So I am going to write down, though, that we have the group size, like the total group size, is 20. And the selection, I could call it, like the smaller group that's being chosen, I'll say we're choosing, how about I'll say it this way, choosing 3. Oh my goodness, come on. Sorry, my camera. Why? It keeps doing this. All right. All right, I think it's better now. Okay, so does order matter here? Does order matter? Well, they didn't say that these three positions are ranked, right? So remember, when you're thinking, does order matter? You're thinking about the things being chosen, right? Are they like first, second, third place, right? Is there anything going on like that? And the answer is no, right? It's just three people that are being chosen from a group of 20. So this is not, these positions are not ranked. So we're going to use, switch colors here. We're going to use the combination, we're going to use the combination of 20 and 3. So choosing 3 people from a group of 20. And we know how to do this calculation, right? This is, so what am I doing right now? You know, I was asked to find a probability, so what am I doing with this? Well, this is going to be the size of my sample space. How many different ways are there? Just how many ways total are there to pick 3 people from a group of 20? That's what this question is answering. That is what needs to be in the denominator of our probability fraction. All right, since we've already kind of talked about this a fair bit, I'll just go ahead and say this is going to be 20 times 19 times 18 over 6. Let you fill in that arithmetic in between. And then, well, I am going to need to ask the calculator to do this for me because I don't feel like doing it in my head. And I'm getting 1,140. So again, let me write down what this represents. There are 1,140 possible ways ways to choose 3 people from a group of 20 when what? When order does not matter. When I say order does not matter, I mean the order of the 3 people. Okay, good. That is the denominator of my fraction. What fraction? The probability fraction, right? Okay, what about the numerator? So this is like denominator in red here. Well, they say, so what is the event? What is the actual event that we'd like to measure the probability of? Well, that's coming from the question where they say, if the names of all the graduate students were put in a hat and 3 were drawn, yes, what is the probability that you and your 2 friends, Leonard and Sheldon, end up being chosen? So how many different ways are there for them to pick you, Leonard, and Sheldon? Well, since there's 3 of you, and you want to get all 3 positions, there's only one way for that to happen, right? There's only one way. I'll say me, so me is the person in the example. Me, Leonard, and Sheldon. Okay, Sheldon. There's only one way for the 3 of us to be chosen. No math really needed for that, just a little bit of thinking, right? There's only, now if we were picking 4 people from a group of 20, right, then it could be me, Leonard, Sheldon, and then someone else, right? And it gets a little bit more complicated there because then how many ways is there for that to happen, right? So that's a little bit of a brain teaser there. But in this case, there's just one way. There's just one way for the 3 of us to be chosen if 3 people are getting picked, right? And I again specifying that order is not important, so it doesn't. I'm still counting it as 1. For instance, if if I'm chosen, then Leonard, then Sheldon, versus if I'm chosen, then Sheldon, then Leonard, or Leonard, me, then Sheldon, etc. Those are all still the same thing. It's all just counting as 1. The 3 of us is counting as just 1. So that means that my probability. So P of, and then you're supposed to put the event in parentheses here. You kind of get to name it whatever you want. A lot of times, I think I've said this before, that the event will just be named as the capital letter E so that you can just put an E here. But you can write out like probability of all three, I'll say, of us being chosen. Godly, why is my spelling like, I know how to spell these words, I just like writing and thinking and talking all at the same time and trying not to knock over my microphone, all these things. Okay, all three of us being chosen should be equal to 1, that's that one in blue, over 1,140. That's it. See, all the hard work, really the weird hard work, the weird math happening back here is where we know it from 7.2, right? Okay. And by the way, what is that probability? It's, well, as a decimal, you could say 0.000877. And then that as a percent, that is equal to, as a percent, 0.0, let's see, 877%. In other words, the chances are extremely low that this would happen, that all three of these people would be chosen. Okay. So I want you to note, though, that the new stuff is happening in blue here, right? We already know how to do probabilities. We've already been introduced to this fraction, right? We've already looked at how to count things like this. The new thing is just kind of bringing this sort of knowledge, right? Kind of thinking about things critically. Let's keep this going by looking at an example that is going to use a permutation to count these sample space. Also, I apologize for all the harsh shadows. I usually record during the day when the sun is out, and that gives me a lot of natural light in this room, but it's pretty late right now, so it's dark out. So it's lots of harsh shadows coming from the overhead light. Okay, so example 2 from the text says, let's change the previous example slightly. Suppose that as one of the 20 graduate students in the physics department, you have a chance of being selected for one of 3 student spots for a conference in Cancun. So there's still group size is 20. Okay, so that didn't change. And we're choosing 3 still. Sounds the same so far, but let's see what happens. The names of all students are put in a hat and 3 are drawn. Okay, however, if your name is drawn first, you get all expenses paid. If you are chosen second, everything is paid for except meals, and if you are chosen third, you must pay for your own meals and hotel. So the positions are ranked this time. Being chosen first is the best, right? Positions are ranked this time. Whoops. Positions are ranked this time, and that should make you think of using a permutation. But let's see what the, we haven't even looked at what the question is, like what probability are we measuring? So let me read on. What is the probability that you and your 2 friends, okay, so still Leonard and Sheldon, so the 3 of us, all end up being chosen, and that your name is drawn first? Okay, so that might get a little complicated with that numerator, right, that event that we're measuring. But I know that my denominator should be a permutation. It's just like the last one, except that order matters this time. Order matters this time. So this is going to be 20 factorial over 20 minus 3 factorial. And just to save, whoops, that's just equal to this, right, over, well, I don't need a fraction anymore once I do the canceling there. Again, I'll let you work that arithmetic out, or you can ask me in class if you're unclear about where this is coming from. We can definitely do that. All right, and that is 6,840. Okay, there are, let me write down what this represents. There are Okay. So there are this many ways to choose 3 people from a group of 20 when order does matter. Because now the different choices are distinct. Like me, Leonard, Sheldon is distinct and different from Leonard, Sheldon, me, right? So those are all counting as different different choices. So that's why there's a lot more than the last example when it was 20C3, right? Okay, so that's going to be our sample space, or rather our size of our sample space. What about this numerator? How many ways can this event happen that they're describing? So the event they describe is not only just the 3 of us being chosen, but also that our name, meaning me, myself, or you doing this problem, whatever, is drawn first. So how many ways are there for the 3 of us to be chosen? Surely it's not that many. Let me lay them out. First, it could be me, so that's me, Leonard, Sheldon. Then it could be me, Sheldon, Leonard. So I'm using S and L to denote them. So Leonard, Sheldon, Sheldon, Leonard. What else? So those are the 2 that can happen with me being first. These are the ones that we want, really. But can we list the rest of them? What if Leonard's first, and then me, and then Sheldon? And then if Leonard's first, and then Sheldon, and then me. And then I think you get the point that the last 2 combinations would be Sheldon first, then me, then Leonard, or Sheldon first, then Leonard, then me. But what did they specifically ask? So these are the number of ways that the 3 of us can be chosen in these different orders. They said all of us end up being chosen, right? And that your name is drawn first. So we want either this category. How many ways are there to do that? 2. And there are 2 ways for the 3 of us to be chosen and for my name to be first, right? Because there are 6 ways for us to be chosen, but I want my name first, so there's only 2 ways for that to happen. So this probability I'm gonna be lazy and I'm gonna say up here, let E be the event of the 3 of us being chosen, blah 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 blah. Let E be the event of So that means I'm just naming the event so that when I write P of event, probability of event, I don't have to write all this junk in there, which just kind of looks bad, right? I can just write P of E. It's much more compact and pretty looking. And it's going to be a fraction of 2, right? 2 coming from that event space that we described, these 2 possibilities, over 6,840. Coming from there, right? The number of ways that there are to pick 3 people from a group of 20. All right, good. So we're getting that this is, let's see, this is 3 times as small, so getting like approximately 0.000292, which is equal to 0.0292%. So an even lower chance, because if you recall, the last one was like 0.087%, and this is 0.029%. So of course we expect this to be an even lower chance here. Cool. I should say in any case, these are both extremely unlikely. Right, so just to, let me recap that just in case you've forgotten that sort of like intuitive idea about probability. 0 or 0% means a probability of some event E being 0 or 0% means E is impossible. So when something is barely above 0, that means it's extremely unlikely. It's extremely unlikely. I didn't mean to put that dot there. So a probability of 0 would mean just not likely at all. I mean, in fact, impossible. And a probability of 1 or 100%, whatever that event is, means E is definitely going to happen, like for sure going to happen. Definitely going to happen. So that means, you know, when we, like if I put it on a number line, here's 0 and here's 1. So this is for sure going to happen, this is not going to happen at all. The two probabilities that we just measured were like 0.000292 and 0.0008, whatever. So it's like, I mean, I can't even like describe how close to 0 that is with a picture, right? So those events in example 1 and example 2 are extremely unlikely. Because they were so small. All right, now I'd like to look at example 4 from the text. So if you're following in the text, we're now looking at example 4, and you will want to follow in the text because I'm going to be citing a table that they're using there. So yes, I am skipping the complement example. I mean, maybe I'll define complement later or something. I just don't think it's like explicitly necessary for us right now. It's very intuitive though, and it's fine, but I just, for now, I don't want to derail us from calculating probabilities by giving you a new definition to think about. So I'd like to skip example 3 and that definition of complement, at least in this video, and go straight to example 4. So example 4 cites this table. It says U.S. import destinations by weight in pounds for fresh or dried walnuts and pistachios from the years 2006 to 2011. So when they say U.S. import destinations, they mean like where the nuts are coming from somewhere to the U.S. Okay. So part A says. So I'm not gonna draw that table. So go pull it up in the ebook in Hawks. It's on page 330 in section 7.3. All right. So part A says find the probability that the walnuts you consumed during this period were from Australia. No, just Austria. So I will write that question down. And when it says the walnuts you consumed, they're making a strong assumption here that we were in America from the years of 2006 to 2011, which may not be true, but just, you know, play along for the sake of this problem. So find the probability during this period, so during the period of time, so during this period. We're from Austria. So again, we're assuming that we were living in America. All right, so looking at this table, I see that there are five countries, and then another another category that just is labeled other countries. And I'm specifically looking at the walnuts section because they asked about walnuts, right? So the top half of the table just dealing with walnuts. So I can show you here on video if you're able to see that. Oh, that's not bad. I think we can make that out if my camera will focus. So I'm looking here. There's India, Mexico, Spain, China, Austria, and then other. And then we have numbers corresponding to each of those. Okay. So, if we want the probability that the walnuts you consumed during this period were from Austria, then what we want is the total number of walnuts possible that came into the U.S., and that'll be the size of our sample space. That's the total number of possible destinations and such that the total number of pounds rather that came into the U.S. from different locations. So I'll say total walnuts should be from India. We had 4,373. And then Mexico, we had not so many, 1,268. Spain, 5,239. Okay, so they export a lot of walnuts. China, 1,533. In Austria, 1,938, so 1,938. And then from other countries that didn't make it to the table, 4,157. Okay, that's going to be equal to 18,508. That's my total. This will be the size of my sample space. Okay, now, second part of this is to find the number of walnuts that could have come from Austria. Well, that's just straight from the table. Walnuts from Austria was 1,938. So the probability of where my event is getting walnuts from Austria is equal to that number of walnuts that came from Austria divided by the total number of possible walnuts that made their way into America, but in this time range of 2006 to 2011. And what does this calculate to? So again, just pop it into the calculator, and I should say approximately 0.104711, or that is also that is 10.4711%. Okay. Part B. Part B says, find the, here we go. There we go. Find the probability that the walnuts you consumed were from somewhere other than Austria. Okie dokie. Total is the same. Oh, wait. Yes, still dealing with walnuts. So total is the same. What was it? It was 18,508 from last time. Now this time, we want walnuts from somewhere other than Austria. So that's all of the places except for Austria. So everywhere except Austria. So that would be, if I calculated that, and minus, so I'm just subtracting out the Austrian nuts. That's one way to do it. And I'm getting 16,570. So just the most straightforward way to do it is to add up all of the walnuts except the ones from Austria. Okay, then my probability of getting not from Austria, right? Because that's what I'm measuring here. Is going to be that 16,570 divided by that that total 18,508. And this is giving me approximately that. So let me double check, because that's what the 89528 and they round up. Yep, okay, which is equal to, as a percentage, 89.5289%. Okay, so pretty high chance. There's like a 10%, what was it for part A, like a roughly 10% chance that one of the walnuts that you consumed were from Austria, and the opposite, 89%, roughly 90%, that they were not from Austria. Now, it's no coincidence that if you add these two numbers together, that you would get 100%. That's no coincidence at all, because these two events are called complements of each other, and the book solves it by making use of that. So again, I didn't want to define complement here, so I solved it more the straightforward way. But we can discuss that later. All right, now part C. C says, assume that you also purchased pistachios during this time period. What is the probability that the pistachios came from somewhere other than Italy and Switzerland? Okay. So find the probability that the pistachios you consumed were from somewhere other than Italy and Switzerland. So we're trying to discount Italy and Switzerland. But note that we're talking about pistachios this time, so I need to redo my total because it's a different total. So finding the total pistachios, I would add up 2012 from Iran, 2030 from Turkey, 262 from Hong Kong, 64 from Switzerland, 115 from Italy, and 323 from other countries. And this is giving me a total of 4,806 total pistachios. Now, what about my numerator for the probability? How many ways are there to get pistachios? In other words, how many pounds came from places other than Italy or Switzerland? So that would be from Iran and Hong Kong. No, sorry, I skipped Turkey. So from Iran, then Turkey, then Hong Kong, which is 262, then skipping Switzerland, skipping Italy, and then the 323 for other countries. And that's giving me, what is that giving me? Let's see, I'll just do that real quick. 2012 plus 2030 plus 262 plus 323. And I'm getting 4,627. So you know what? Let this be called E, this event. So I don't have to rewrite it. Let this be E, just to save myself from writing it all over again. So it's not that the number is E, right? I'm just naming the literal phrase E so that I don't have to write it in my parentheses. Okay, so that's going to be like this, and it's going to be that number of ways to get pistachios not from Italy and Switzerland over total. So these are pretty close to each other, so we expect this to be a pretty high probability. Let's see, 0.962755, which is equivalent to 96.2755%. Nice. Okay, so that is the last example for this section. In the homework, I gave some problems to look at for review. I need to fix those. I'd like to not give you 7.3, 14, and 15 because I did say, and I'll put this in the Teams chat as well, I said do these, but I'd like to change my mind because they don't really reflect. They're more difficult than what I'd like for you to be prepared for on the exam. Numbers 3 and 7 are more like what you need to look at. So I'll be sure to tell you outside of this video too about that. But yeah, so those are some problems you could look at for exercise. Really any of those, well, some of them do get quite tricky. The textbook does not have great problems. So at least look at those. All right, that's it for 7.3.